Okay, fine. So these are some of the drawbacks of the Bezier curve. There is no local control, right? Uh, so far we discussed about all these things, but I forgot to record that. So this is one of the major drawback, and second one is curve doesn't pass through all the control point. It is always passing through the first and last point. So nothing but the approximation based curve, right? So in certain cases it can be a drawback for the Bezier curve as well. And degree of the equation depends upon the number of control. This is very important drawback. Just now I told you, right? If you take 10 control points, for example, the degree of the equation would be very high, which means you may go up to 1 minus u to the power of whole to the power of 9. So which is difficult for the computer or for anybody to solve various points and then play with the points, all the control points. It's very difficult if you go with the higher degrees of the equation. So which is another big drawback of the Bezier curve. So that's the reason for a higher number of control points, the people don't prefer a pure Bezier curves, and the higher order curves are more wavy. Yeah, higher order curves also more wavy when we, in case of a Bezier curve. Now we are going to talk about the synthetic curve, third synthetic curve called B-Spline curve. B-Spline curve. So all the drawbacks and the advantages that we discussed of the about the Bezier curve, all advantages can be continued. At the same time, the drawbacks like degree of the equation can also be reduced. In case of Bezier curve, degree of the equation purely depends upon the number of control points. But here there is a possibility to uh, to have your own degree, to specify your own degree of the equation. Okay, there is a term called, there is a new term called order. Okay, would be introduced, order of the curve would be introduced on top of the number of control points. Okay, total number of control points are n plus 1, and there is another term called k, which also would be uh, another parameter given to the B-spline curve. Okay, we will talk about all these things now. From this picture, let us try to understand some of the things. So here you can understand that the original points are, the original control points are P0, P1, P2, P3, P4, P5, P6, P7. How many control points? 7 plus 1, 8, total 8 control points. And the curvature is, if you look at the spline, if you look at the original spline formed with the help of all these 8 control points, is something like this. This is the one, this is the original one, this curve. You can understand, you can understand the path of that curve. That is the original curve. But now what I'm doing is, this particular P3, let us say the point I just moved, I just shifted to another location, to this place. Now if you try to understand the influence of this movement, the influence of this P3 on the overall curve, only certain portion of the curve, only certain, probably starting from this location to this location, only this portion of the curve alone got shifted towards the new location of the P3 dash, whereas remaining portion of the curve, for example, starting from P7 to this portion, this curve doesn't change at all. So the point, similarly, the point can also be altered downward, can also be moved downward to this location from P3 to P3 double dash. Another location also I can move. So here also the effect of the control point is, it is limited to only certain portion of the curve rather than the entire curve. This is the beauty of the B-spline curve. You can decide how many each control point, how many segments it can influence. You can decide on the B-spline curve. So which is nothing but local control is possible in case of B-spline curve, unlike the global control of the Bezier curve. Similarly, there is a B-spline curves. You can play with B-spline curves by changing the k value. As I told you, k is nothing but the order of the curve, right? So this is new term that would be introduced in case of B-spline curve, denoted with the k. So if k is equal to 6, if k is equal to 6, okay, what do you mean by k? What do you mean by k is you can understand the k value by with the help of segments. With the help of segments. Segment means the entire curve, the overall curve would be divided into number of segments. In case of B-spline curve, overall curve would be divided into number of segments. Okay, for example, here the number of segments and all, there is a formula for the number of segments, n minus k plus 2, n minus k plus 2 gives you the number of segments. For example, here n is, what do you mean by n? N comes from the number of control points. Here the number of control points are 1, 2, 3, 4, 5, 6, 7, 8. It is starting from 0, right? 0 to 7 means total control points are 8, which means n plus 1 is equal to 8. Always control points are n plus 1. So n plus 1 is equal to 8, which means n is equal to 7. So if you substitute that, 7 minus k, for example, if k is equal to 6 here, if k is equal to 6 means n minus 7 minus 6 plus 2, which means 3. I am getting total 3 segments, which means if for this case n is equal to 7, k is equal to 6, the curvature, the entire overall curve would be divided into 3 segments. Overall curve would be divided into 3 parts, and all the 3 parts, if you join all the 3 parts, this is how the curve looks like. You can imagine there are totally 3 curves that you can see, three major curves that you can observe. So this curve, this curve is made with this curve starting from P0 to P7. That overall curve is made with the 3 segments. Each segment is influenced by how many, what is the k value? Corresponding k value is 6, right? So each segment is influenced by 6 control points. Okay, so k is order, right? So you can understand that the k value, it is actually deciding the overall number of segments, and also each segment is controlled by how many number of control points. That also you can understand from the k value, but which may not be the same. This is in case of a uniform B-spline curves. Whatever that I told you right now, that happens in case of a uniform B-spline curves. In case of a non-uniform B-spline curves, the each segment may be influenced by, of course, in non-uniform also the same thing happens. Each segment would be influenced by the number of control points, k depending upon the k value. Okay, but there is a difference between non-uniform and uniform, which we'll discuss in the subsequent slides. Don't worry. And similarly, if k is equal to 4, if someone asks you to find out how many segments are there, again substitute the n value is 7 minus 4 plus 2, you get 5, which means this curve is made with the 5 segments of the overall curve. Similarly, by changing the k value, the overall shape of the B-spline also changing. So this you call it as a family of B-spline curves for different k values. Okay, and another thing that you can understand from the k itself, from k, another thing also that you can understand. Look at here. If k is equal to 3, he is saying that quadratic. He is saying quadratic. If k is equal to 4, he is saying that cubic. What do you mean by that? So for k is equal to 3, the maximum degree of the equation would be, quadratic means 2, right? Quadratic means 2. So the maximum degree of the equation will go up to 2 only. If k is equal to 4, the maximum degree of the equation will go up to 3 only. So here there is a possibility for you to even reduce the degree of the equation also. So degree of the equation is simply nothing but degree of the equation is simply nothing but k minus 1. So that is the reason for k is equal to 3 you are getting quadratic, for k is equal to 4 you are getting cubic, for k is equal to 6 you are getting quintic, which is nothing but the degree of the equation goes up to 5, which is 1 minus u to the power of 5, such kind of equation. So It is up to you what kind of degree, what kind of order that you want to, assign to a particular curve, and depending upon that you can solve the equations, various varieties of the equations. Are you following? Is this clear to you? And B-spline curves, there is you can even, just like a Bezier curve, you can uh, by uh, by picking the same starting and end point, you can get a closed Bezier curve, right? Similarly here also, even B-spline curves also, the same point you can pick it, you can pick as a starting point as well as the end point, P0, P1, P2, P3, P4, again P5, I'm picking the same point. By picking that, you can get a B-spline like this. But here, if you try to understand the difference between this one and this one, here both the starting point and ending point are same, but there is no tangency at all. Okay, the tangency is not maintained, so that's the reason it is very sharp at this point. The entire curve is very sharp. So which is, but just they joined, so that is nothing but C naught continuity. So B-spline curve, a closed B-spline curve made with a C naught continuity means at the closing portion, the curve would be very sharp. Similarly, whereas if you go with the C1 continuity, means at each and every point, you should maintain the common tangency also. So that is the reason the curve comes like this, and also it will be a smooth. It will be a smooth, much a smooth tangency maintenance. Okay, slope would be maintained, a common slope would be maintained at the P0 P5 portion also. But the problem here is, uh, you know here what happens is, look at here, P0 and P5, they are also think depending upon the type of polygon, okay. See, the type of continuity depends upon, again it depends upon the k value. The type of continuity, that again depends upon the k value. The continuity, if we said like k is nothing but the order, right? K minus 1 gives you the degree, k minus 1 gives you the degree, and k minus 2, further if you reduce one more value, k minus 2, that k minus 2 decides the kind of continuity. K minus 2 decides the kind of continuity. So depending upon the k value, sometimes the kind of continuity is possible, sometimes it may not be possible. Okay, depending upon the selection of the k value. So you can understand that you can create a closed B-spline curves also using first and last, by picking the first and last points in the same manner. Now coming to the some of the characteristics of the B-spline curve. So far whatever that we discussed, all those things comes here. Local control is possible. Okay, characteristics of the B-spline curve. So coming to the B-spline, mostly you don't get a problem. You will get a theoretical kind of question from the B-spline curve. So try to understand these points, and more emphasis I am putting on the concept itself rather than trying to solve a problem. Okay, so local control is possible. Just now we discussed each control point is associated with a unique basis function. Each control point, every control point will have a unique association with a basis function that you will understand once we talk about the parametric equation. Now control points are denoted with the overall control points are n plus 1, order of the curve is k, degree of the curve is k minus 1, and I said like continuity is k minus 2. You can include that one also here as a characteristic of the B-spline curve. And curve is made up of n minus k plus 2 segments. I also told you about this one, n minus k plus 2 segments. For example, if you look at this right side picture, here it is said that overall control points 1, 2, 3, 4, 5, 6. So total control points are 6 control points, and k is equal to 4 for 6 control points, and k is equal to 4. That is how the B-spline curve is looking like. Let us see the number of, here in the B-spline curve, he also showed you the segments as 3, right? Look at here, this portion is in red color, whereas this portion, this segment is in blue color. There is a third segment which is again in the third. So totally the total segments are 3, which you can again verify from this equation, n minus k plus 2, you should get 3, right? So if you try to substitute these things in this formula, if the control points are 6, n is equal to 5. Why? Because control points are n plus 1, always n plus 1 denotes the control points. So n plus 1 is equal to 6 means n is equal to 5. So I just use 5 here, minus k is equal to 4. For this diagram, k is equal to 4, that is taken, okay, plus 2. So this gives the overall number of segments of the final curve. So that is the reason the B-spline curve is divided into 3 segments. Each segment would be controlled by, again, each segment would be controlled by how many control points? The k. If k is equal to 4, so each segment would be controlled by 4 control points in this case, in this particular case. For example, this red color portion, first segment, red color portion of the curve, first segment of the B-spline curve would be controlled by P naught. Okay, let me write values: P naught, P1, P2. These are P's. Okay, P2, P3, P4, P5. So total control points are 6, starting from 0 to 5, right? So if you look at the first red segment, first segment of the curve, that would be made by P naught, P1, P2, P3. Using these 4 control points, the first segment would be created. Similarly, the second segment, the blue color one, would be influenced by again 4 control points, which are 1, 2, 3, 4. Look at here, P1, P2, P3, P4. These 4 control points influence the shape of the second segment. And similarly, starting from 2, 3, 4, 5, these 4 control points influence the shape of the third segment. Okay, which means each and every control point doesn't have influence on each and every segment. For example, if you take the point 5, even if you move to some other location, the point 5, as we discussed, it has influence only on the last segment, which means even if you move it, the shape of this blue colored one and the first red colored one, they don't change. Only from here, a new segment of the curve would be generated depending upon the new location of the 5. So that you can understand from here. And another thing is this the present B-spline curve, which is passing through the first point as well as the last point, which is passing through the first and last point. When it is happening like that, you call it as a non-uniform B-spline. Why? Because each and every control points are not having the similar kind of influence on the overall shape of the curve. Okay, so that is the reason it comes under non-uniform B-spline. And in majority of the cases, the user requirement itself would be something like he wants to create a B-spline curve which passes through two endpoints. So in that case, definitely we need to go with the non-uniform B-spline curve only, unless otherwise some specific requirement comes for the uniform B-spline curve. If you take a uniform B-spline curve, each and every point behaves in the each and every control point behaves in the which means its influence would be the same. Its behavior would be the same, not influence on the overall curve, but its behavior would be the same. and the curve doesn't pass through any endpoints also in case of a uniform B-spline curve. So all those things are characteristics of B-spline curve, which you can observe here. And there is another thing called n plus k plus 1 knots. N plus k plus 1 knots are required to generate k minus 1. As I told you, k minus 1 tells you the degree, right? K minus 1, here itself it is said. K minus 1 is the degree curve defined by the n plus 1 control point. So there is a new term called knot. So that would be used, knot vectors are also used for a B-spline curve for a for parametric representation, mathematical representation of the overall B-spline curve. So an overall number of knots are n plus k plus 1 knots are required. That's what he's saying. So now coming to the parametric representation of the B-spline curve, it looks bit difficult, but most of the terms are when you try to expand. If you look at this one, P of u is equal to sigma I is equal to 0 to n BIK. Look at here, BIK. Earlier in case of Bezier curve, it was BIN, right? So it is now it is BIK of u into PI, and where u is varying from 0 to a maximum value. Whereas in case of Bezier curve, it was 0 to 1, 0 to 1 if you can recollect. But here in case of B-spline curve, u maximum. What is this u maximum? It is again, u maximum is nothing but number of segments only, which is n minus k plus 2. For example here, 1, 2, 3 segments, right? So u varies from 0 to 3. U varies from 0 to 3. U is equal to u for the first segment of the curve. U varies from 0 to 0 less than or equal to u less than or equal to 1 for the first segment, which means u is equal to 0 here, u is equal to 0 here, and at the last endpoint of the first segment, u is equal to 1 here. Okay, so this is one portion, whereas u varies from 1 to 2 for certain other segment, certain for the second segment. Similarly, from u varies from 2 to 3, u is equal to 3. So unlike the Bezier curves where u was varying from 0 to 1, but here there is a maximum value which is equal to the overall number of segments, which is whose equation is equal to n plus n minus k plus 2. So that is another difference that you can understand. And this order, the least value for the k is equal to k is equal to 2 always. It's a constant value. Why? Because if k is equal to, let us say if k is equal to 2, which we are saying that it's the least value. Why? Because if k is equal to 2, the degree of the equation will be 1, and the continuity of the equation would be again 1 more minus is equal to 0. So C naught continuity is the least continuity that any curve should maintain. Otherwise, there won't be any continuity at all. So that is the reason the least value for the k is equal to 2. It starts from 2, and the maximum value it can go up to n plus 1. So whenever you select a k value for any curve, B-spline curve, you need to make sure that the k is varying in between 2 to n plus 1 means control points. Otherwise, you cannot frame the B-spline curve at all. So in this parametric equation, there is a term called BIK of u. This term, there is an expansion for this BIK. Wait a minute. So the expansion for this term is you can get it. Okay, just a minute. Okay, fine. Just like the blending functions of Bezier curve, here also another terms are there. Another terms are there denoted with the BIK of u, which are expanded. Expansion of BIK of u is this way, right? Let me continue. Fine. Actually here, if you try to understand BIK of u, BIK of u can, if you want to calculate BIK of u, it depends upon BIK minus 1 of u. Look at here. This is also another term of the same kind. Again, both are of the same. So in order to solve BIK minus 1, again you need to use the similar kind of equation, which may come like BIK minus 2 in terms of k minus 2. So similarly here also you are getting another b value bi plus 1 k minus 1. Again this is also of the same kind. So that is the reason this equation is of recursive form. This equation is in a recursive form, and that recursion should end somewhere. So that recursion ends here. In order to end that recursion, we are using this these values at bi1. When you try to expand all these formulas, by writing so many equations, at some point of time you will end up with the bi1 of u, and whose value will become a constant, will be taken like either 1 or it will be 0 depending upon the u value. And ui, this ui denotes the not vectors. Ui denotes ui. Here we are using ui, right? This ui gives you the this is a new term. It's not related to u at all. Instead of ui, in some of the textbooks they use ti or any other term also they use. Okay, why? Because this is totally a new term, which is to denote the, which is to include the not vectors. Okay, so those not vectors also can be calculated. Not vectors also can be calculated using the subsequent equations given here. So this is the not vectors also can be calculated. All these values are constants only. For example, uj you want to calculate the j value you will supply. For example, u3 you want to calculate, right? For example, u3, which is one of the not vector, if you want to calculate, and so that you can substitute in this b function. So if you want to calculate u3, j value is equal to 3, and k is a constant value. Similarly, n is also a constant value. So all these equations are by calculating, first of all you need to verify whether j is equal to, whether this particular 3 value, whether it is less than k value, or in between k to n value, or whether it is greater than n value. You need to verify, and depending upon that j value, you need to make use of whether u3 will be 0 or u3 is equal to, you need to use this formula or this formula. So which formula you need to use, it depends upon the j value. So these not vectors can also be calculated and then substitute them in the polynomial function b function. So that is how this is the parametric equation. Of course, it looks like a tedious process, and frankly speaking, if you want to solve it manually, it may be a very tedious process. So but because of the various advantages of this, once the evaluation of the computers could help the industry to develop such kind of complicated curves also, which can give which is very highly flexible, which can accommodate many varieties of the requirements of the users, designers. Okay, for computer, such kind of recursive functions can be easily solved using programs, right? So you can I want you to remember, and also should be in a position to if some questions are asked, then you at least you should be in a position to say something about all these parametric equations. Okay, now there is a last synthetic curve called NURBS, which is the expansion form of NURBS is non-uniform rational B-spline. Okay, non-uniform rational B-spline. Earlier we were talking like non-uniform B-splines, right? Non-uniform B-spline. This is a non-uniform B-spline. Why? Because it is passing through some of the control points, and the influence of the control points are different. They are not same across all the segments of the curve. So this is non-uniform B-spline. But there is a new term called rational. Okay, there is a new RBS, right? So R denotes a rational. R denotes rational. What do you mean by this rational? How to incorporate this rational is by, here there is another term called WI. WI. What do you mean by this? WI is weightage. You can provide weightage. You can play with the weightage given to different control points also. So that is the beauty of this NURBS curve. NURBS curve. So you can increase the certain weightage. For example, let us say for a particular weightage given to these control points, let us say this is how the NURBS curve got created. Let us say for this P2 control point, I want to assign more weightage. I want to assign more weightage. If you assign more weightage, then what happens to this curve would be the curve moves towards moves towards that point. Okay. Why? Because more weightage is given to P2, and indirectly saying the other control points have less control over the shape of the overall shape of the curve. This P2 do have a more curve. Similarly, if you assign more weightage for this control point, the shape of the curve moves towards this point. Why? In certain design practices, the designers do the designers specifically ask such kind of requirements, like they want to move the overall curve through a particular point, which means they want to give a lot of infinity weightage to that particular point. Then the overall curve also passes through that control point, or at least it moves very near to that. So such kind of special requirements are possible in case of a NURBS, which is expansion for the B-spline curve by incorporating a weightage WI. If all the weightages are same, let us say all the weightages are 1, then the bottom denominator will be equal to, finally it will be equal to 1, and you'll be left with only the the numerator term without any WI. Why? Because the WI is equal to 1 if you use it, and which is exactly, this equation is exactly same as the B-spline curve. So some characteristics, if you want to try to understand NURBS, about NURBS has more versatile modification capacity, because you can play with the weightages given to control points also, and can exactly represent conic curves, circles, ellipses. Yes, which means this NURBS, this equation can accommodate any kind of curve. This or of this final parametric equation, this can accommodate, which means any kind of even if you take a circle, even for circular equation also can be written into this form. This form can accommodate any kind of whatever the curves that we discussed so far. Whether it is analytical curve or synthetic curve, all the curves can be written into this form, which is nothing but this NURBS. That is the reason NURBS is considered as a superset. It is considered as a superset of all curves. Using this form, you can derive B-spline, you can derive Bezier curve, Hermite cubic spline, any kind of curve you can write it. Even if you can make analytical curves, you can prepare analytical curves also. Like conic sections, ellipse, parabola, all these things are also possible using simple NURBS curve. Okay, with this I am concluding. Today's session, and I also prepared. I also, whatever the lectures that that are given to you so far, all the lectures. Of course, I missed some of the lectures to record, but most of the lectures are recorded. And I also uploaded all the lectures into one channel, which you can make use of this channel also. Okay, and I will post this channel link in the chat box, and you can go through. Okay, and of course, here itself I'm telling these are all only the recorded lectures, which you should not compare with other lectures. Why? Because generally in YouTube, the topics, all the videos are the topic wise, and the entire concept cannot be covered in 10 to 15 minutes, right? So here only the recorded videos alone I just uploaded, and whoever wants it, you can make use of those videos. Okay, fine. This